Module 2, Lecture B, Math for Analysis. By the end of this lecture, you will be able to use basic properties of logarithms and exponentials to interpret algorithm complexities, evaluate simple arithmetic and geometric series that arise from loop counts, and solve or approximate simple recurrences that describe divide-and-conquer algorithms. Logarithms in algorithms. Log bases and constants. In algorithm analysis, logarithms often appear, and while mathematics commonly uses base 10 or base e, computer science naturally uses base 2 because of binary operations like repeatedly halving a search space. However, the specific base of the logarithm does not affect how we classify an algorithm's growth rate. Changing the base only multiplies the logarithm by a constant factor, and constant factors are ignored in big O notation. As a result, whether you use base 2, base 10, or base e, the overall growth behavior of the algorithm as the input size increases remains the same. In algorithm analysis, a logarithm tells us how many times we must repeat an operation, such as halving or dividing by 10, to reduce a problem to a certain size. Using base 2 fits repeated halving, while base 10 fits repeated division by 10. But these counts differ only by a constant factor. This is similar to converting between miles and kilometers, where the numbers change but stay proportional. Because we care about how running time grows with input size, not about constant factors, all logarithmic bases are treated as essentially equivalent in this context. In algorithm analysis, the base of a logarithm only changes the result by a constant factor, so we usually ignore it in big O notation. A running time that is a constant times a logarithm often reflects implementation details, such as how many operations each step performs, or hardware differences. Two algorithms might both cut the problem size in half each step, yet one can still be slower because each step does more work, giving it a larger constant. These constants matter for actual performance, but big O notation focuses on how the running time grows overall, which is why logarithmic algorithms are considered efficient compared to linear or exponential ones. Python code, log bases and constants. This section explains how different logarithm bases affect algorithm analysis. It compares how many steps an algorithm takes when the input size is repeatedly cut in half versus divided by 10. The key idea is that changing the base of the logarithm only changes the running time by a constant factor, not the overall growth trend. Any notes about installing extra libraries are not necessary for understanding this concept. We begin by loading the math module so we can use its built-in logarithm functions with different bases. This is necessary for carrying out logarithmic calculations in our script. With these tools available, we can examine how changing the base of the logarithm influences the growth rates of algorithms. We begin by defining a list of input sizes that represent different problem scales measured in numbers of elements such as 10, 100, 1,000, and 10,000. These values serve as our test cases for examining how the number of logarithmic steps changes when we use different bases. By comparing these steps across growing problem sizes, we can see how logarithmic behavior depends on both the base and the size of the input. The code first prints a header line that labels the columns of a comparison table. These columns show the input size, the number of steps based on a base 2 logarithm. the number of steps based on a base 10 logarithm, and the ratio between these two logarithmic values. This header prepares the listener to understand what each column in the upcoming output represents. We loop through each input size so we can analyze every problem size separately. For each one, we calculate logarithms with different bases to see how the number of steps changes when the base changes. This helps us compare algorithms that shrink the problem by different factors, such as cutting it in half or dividing it by 10. Overall, this setup lets us study how the choice of reduction factor affects algorithm efficiency. We calculate the base 2 logarithm of the value n to find how many times it can be divided by 2 until it reaches 1. This measure is often used to describe the complexity of algorithms that repeatedly split a problem in half, such as binary search. To perform this calculation in code, we use the logarithm function from the math module and specify 2 as the base. We take the base 10 logarithm of the value n to estimate how many times we can divide n by 10. Using the log function from the math module with 10 as the base gives this measure directly. It tells us how the number of required operations grows when the problem size is reduced by a factor of 10 at each step. This helps describe how the algorithm's work scales as n changes. We are comparing two logarithms by taking their ratio. One logarithm uses base 2 and tells us how many times we can have a number, while the other uses base 10 and tells us how many times we can divide the number by 10. When we divide the base 2 logarithm by the base 10 logarithm, we get a constant factor that links these two bases. This shows that although the bases are different, their growth patterns are the same up to this constant scaling factor. This line of output prints a formatted row for each input size, showing the size itself, the number of steps based on logarithm base 2, and the number of steps based on logarithm base 10, all rounded to 2 decimal places. It also includes the ratio of the base 2 and base 10 logarithms. Together, these values make it easy to directly read and compare how the number of steps changes between the two logarithm bases. The final note explains that the ratio of logarithms with different bases stays constant for all input sizes tested. This shows that changing the base of a logarithm only changes the constant factor, not how fast the function grows overall. In algorithm analysis, this means the specific base of the logarithm does not matter for understanding the asymptotic behavior of a running time. This script compares logarithms with different bases to show how they affect algorithmic steps for various input sizes. It computes base 2 and base 10 logarithms, which represent how many times you can repeatedly have a number or divide it by 10. The results reveal that although the logarithm values change with the base, their ratio stays constant for all input sizes. This demonstrates that changing the base only alters a constant factor, not the overall growth pattern, which is a key idea in algorithm analysis. Binary search logarithms. Binary search is efficient because it runs in logarithmic time, meaning the number of steps grows very slowly as the input size increases. Instead of checking each item one by one, it repeatedly looks at the middle of a sorted list, compares, and then discards half of the remaining items. Each time the input size doubles, only one extra step is needed. This pattern is described by logarithms and explains why binary search is much more efficient than linear search methods. When you perform binary search on a sorted list, you repeatedly cut the list in half until only one element is left. As the list gets larger, you can halve it more times, but this number grows very slowly compared to the list size. Even going from 1,000 elements to 1,000,000 elements only adds a few extra halvings. This slow logarithmic growth means binary search remains efficient because the number of comparisons increases much more slowly than the number of items in the list. Binary search is like a guessing game where you always check the middle of a sorted range and, based on a yes or no answer, discard half of the remaining options. Each step cuts the possibilities in half, so the number of steps needed grows in proportion to the logarithm of the range size. This logarithmic behavior makes binary search very efficient and is why it underlies technologies such as phone directories and navigation systems. Understanding this idea helps explain why binary search and similar algorithms are so powerful. Python code, binary search, logarithms. Binary search becomes more efficient as lists grow because the number of steps increases only logarithmically with the list size. Each step cuts the remaining list in half, so even very large lists can be searched in relatively few steps. In contrast, linear search may need to check each item one by one, so its steps grow directly with the list size. Comparing the two for different list sizes highlights how halving the list at each step leads to logarithmic running time for binary search, while linear search grows much more quickly. The commented line is suggesting the installation of several common Python libraries used for data visualization and data manipulation, specifically matplotlib, Seaborn, NumPy, and Pandas. This is typically done when preparing a working environment for data analysis. However, the note explains that if you are using Google Colab, you do not need to install these libraries yourself because they are already included. This makes the setup process faster and easier for Colab users. The script starts by importing the math module so it can use built-in mathematical tools. In this program, those tools include logarithm and ceiling functions. These functions are later used to calculate how many steps a binary search will take. Importing the module at the beginning makes these operations available throughout the code. We define a function called linear steps that takes a single input, n, and represents the worst-case number of steps in a linear search through a list of size n. In a linear search, you check each element one after another until you find the target or reach the end. This means the number of steps needed is directly equal to the number of elements in the list. Therefore, the function simply returns n to capture this one-to-one relationship between list size and search steps. The binary steps function estimates the worst-case number of steps needed for a binary search on a list of size n. It does this by using the base 2 logarithm of n to measure how many times the list can be halved until only one element remains. The result is then rounded up to the nearest whole number so that any partial step is counted as a full step. This captures the logarithmic behavior of binary search, where each step cuts the search space in half. We use a list of sizes that includes 10, 100, 1,000, 10,000, and 100,000 elements to compare linear and binary search. These values represent different scales of input size. By testing both search methods on each size, we can see how the number of steps they require grows as the list becomes larger. This helps us understand how their performance changes with increasing input size. The code first prints a header row for a table that labels each column. These labels show the list size, the number of steps for a linear search, and the number of steps for a binary search. This makes the output easier to read and helps you clearly compare how many steps each search method takes for different list sizes. We loop through each list size and print a formatted line that shows the size, a number of steps needed for a linear search, and the number of steps needed for a binary search. The output lines are aligned so the sizes and linear search steps line up in fixed-width columns, followed by the binary search steps. This makes it easy to compare how many steps each method takes as the list grows, clearly illustrating that binary search is more efficient than linear search for larger lists. This line explains that when you double the size of the list, binary search usually needs only about one additional step. This behavior shows that binary search grows in a logarithmic way. In other words, the number of steps increases very slowly compared to how quickly the list size increases. This is what makes binary search efficient for large lists. This script compares how many steps linear search and binary search need as a list gets larger. In the worst case, linear search may check every item, so its steps grow in direct proportion to the list size. Binary search, by contrast, needs a number of steps equal to the ceiling of the base 2 logarithm of the list size, so its steps grow much more slowly. The results show that when you double the list size, binary search adds only one extra step, which makes it far more efficient for large data sets. Tree height and logs. Logarithms appear often in algorithm analysis because many algorithms use tree structures that split problems into smaller parts. In a balanced tree, each node has a fixed number of children. So as you go down each level, the number of nodes grows exponentially. This means the height of the tree increases only logarithmically with the total number of nodes. As a result, operations like searching or inserting in a balanced tree take time that grows with the logarithm of the number of elements, rather than growing directly in proportion to the number of elements. A balanced binary search tree stores words in alphabetical order so that each step down the tree roughly halves the remaining search space, much like binary search in an array. The root holds a word from the middle of the alphabet, and its children split the remaining words into smaller ranges. Because of this structure, even with 1,000,000 words, the number of steps needed to find one word grows only in proportion to the logarithm of the total number of words. This idea underlies systems like file directories and database indexes, where the time to locate an item depends on the tree's height, which increases very slowly as more items are added. Logarithms help us compare different tree structures by relating their branching factor to their height. Trees like bee trees allow many children per node, so they become shorter for the same number of elements, which means fewer steps from root to leaf, even if each step does more work. The height of such a tree can be described as a logarithm, whose base is the branching factor. And changing this base only changes the height by a constant amount. As long as the tree remains balanced, these properties allow algorithms to scale efficiently and handle very large data sets with only a small increase in the number of steps. Python code, tree height and logs. We want to show that the height of a tree grows like a logarithm of the number of nodes. To do this, we compare trees with different branching factors, such as binary trees and four-way trees, and see how their heights change as we add more elements. By examining how many levels are needed to hold a given number of nodes, we can connect the branching factor, the tree height, and logarithms. Simple printed outputs can illustrate how increasing the branching factor reduces the height for the same number of elements, highlighting this logarithmic relationship. The commented line mentions installing libraries such as Matplotlib, Seaborn, NumPy, and Pandas, but explains this is usually unnecessary in Google Colab because they are already installed there. It mainly serves as a reminder for people using other environments to make sure these tools for data visualization and data handling are available. In this particular script, though, these libraries are not actually used directly. Script starts by importing the math module so it can use built-in mathematical functions. These functions are needed to perform calculations such as logarithms and powers. In this case, they are used to compute the height of a tree from the number of nodes and the branching factor. By using the math module, the code can analyze how tree height depends on the size of the tree and its branching structure. We define a tree height function that computes the height of a balanced tree using the number of nodes and the branching factor. It uses the logarithm from the math library, taking the number of nodes as the input value and the branching factor as the base. The result of this logarithmic calculation is the tree's height, meaning the number of levels from the root to the deepest leaf. This works because in a balanced tree with a consistent branching factor, the height grows in a logarithmic relationship to the number of nodes. We use a list of two dataset sizes, 1,000 and 1,000,000, to study how the height of a tree structure changes as the amount of data grows. These two sizes represent a smaller and a larger data set, allowing us to compare their effects. By observing how the tree's height scales with the number of nodes, we gain insight into how efficient operations like searching will be in these trees. The code defines a list of branching factors with the values 2 and 4, representing binary trees and four-way trees. A branching factor specifies how many child nodes each parent node can have in a tree. By setting these values, the code can calculate and compare the heights of trees with different branching structures. This helps show how tree height depends on both the number of nodes and the branching factor. The code first prints a header line that labels the columns of the output. These labels are nodes, branching, exact height levels, and rounded height levels. This header explains what each value in the following lines represents. As a result, it becomes easier to understand and interpret the tree height calculations that the program produces. We examine how tree height changes by looping over different numbers of nodes and different branching factors, which represent different tree types. For each combination, we use a tree height function that applies a logarithm to compute the exact height of a balanced tree, showing that height grows logarithmically with the number of nodes. We then round this exact height up to the nearest whole number and display the node count, branching factor, exact height, and rounded height. This output lets us compare how changing the branching factor affects the height of trees with the same number of nodes, highlighting the relationship between tree structure and logarithmic growth. This line prints a message explaining how tree height affects computational efficiency. A shorter tree height means fewer steps are needed to move from the root to a leaf during operations like searching. This efficiency comes from the fact that tree height grows only logarithmically, compared to the number of nodes. As a result, even as the tree gains many more nodes, its height increases slowly, keeping operations relatively fast. This script shows how the height of a balanced tree grows in a logarithmic way as the number of nodes increases, and compares binary trees with four-way trees. It uses a logarithmic formula based on the branching factor to compute tree height, then evaluates this for 1,000 and 1,000,000 nodes in both types of trees. The results include exact and rounded heights, revealing that trees with more branches at each node have smaller heights for the same number of elements. Because a smaller height means fewer steps to move from the root to a leaf, the script highlights how larger branching factors can make operations like searching more efficient, and illustrates the link between tree structure and logarithmic time complexity in data operations. Series for loop counts. Loop arithmetic series. When analyzing how much work a loop does, we often see a pattern where each step handles more work than the previous one in a steady, linear way. For example, the first iteration might process one item. The second processes two, and this continues until the nth iteration processes n items. This creates an arithmetic series, similar to a staircase or a savings plan, with regularly increasing deposits. Recognizing this pattern lets us describe and evaluate the loop's total work more simply and efficiently. Arithmetic series are important in loop analysis because they describe how work can grow in nested loops, where the inner loop runs a linearly increasing number of times. For example, if the inner loop runs once on the first outer iteration, twice on the second, and so on up to n times, the total work forms an arithmetic series. Similar patterns appear when algorithms gradually expand a window over an array or build triangular structures. In all these cases, the total work is the sum of a linearly growing sequence, which is essential for accurately estimating the algorithm's complexity. When a loop's work forms an arithmetic series, you can analyze its growth without tracking every single iteration. Because the work per step increases in a straight line, or linear, way, the total work grows roughly with the square of the number of steps. We can think of this as the average amount of work per iteration, multiplied by the number of iterations. In algorithm analysis, this means loops whose work per iteration increases linearly typically lead to quadratic growth as the input size increases, and recognizing this pattern helps you predict how an algorithm will scale. Python code, loop, arithmetic series. This example should show how nested loops can produce an arithmetic series pattern in their total amount of work. The inner loop should run one extra step for each step of the outer loop, so the total number of operations grows in a simple, predictable way. You then compare this manual loop count with the result given by the arithmetic series formula to confirm they match. External libraries like NumPy, Matplotlib, or Seaborn are not needed for this basic demonstration. We define a function that measures how many times an inner loop runs for a given input value. Inside the function, we start a counter at 0 to track the total number of inner loop operations. The outer loop goes from 1 up to the input value, and for each outer loop step, the inner loop runs from 0 up to the current outer index. Each time the inner loop runs, we increase the counter by 1. At the end, the function returns this counter, which represents the total number of operations performed by the nested loops. We begin by setting a value of 10, which controls how many times our loops will run. This choice keeps the results small enough to view easily when we print them. The number of iterations will let us clearly see the pattern of an arithmetic series in the loop output. To analyze the nested loops, we first compute the total number of operations they perform. We do this by using a helper function that counts how many times the inner loop runs for a given value of n. The result is stored in a variable that represents the total number of inner loop iterations across all outer loop cycles. This total captures the arithmetic series pattern created by the nested loops. We use a simple arithmetic series formula to find the total number of operations without running every step of the loops. For 10 iterations, we multiply 10 by 10 plus 1. Then divide the result by 2 using integer division. This gives the sum of the first 10 natural numbers. The value we get matches the total number of operations performed by the nested loops, providing a quick way to compute it. The program counts how many times the inner loop actually runs and prints this total. This count is then compared to the value predicted by the arithmetic series formula. By matching these two results, we confirm that the manual loop count and the formula give the same outcome. This verifies that the formula correctly represents the behavior of the nested loops. The code prints the total number of inner loop executions as calculated by the arithmetic series formula and compares it to the total produced by actually running the nested loops. This shows that both approaches give the same result. By doing so, the code makes clear that the behavior of the nested loops follows an arithmetic series pattern, and that the formula accurately captures what the loops are doing. This line prints a message that explains how the nested loops relate to an arithmetic series. It shows that the loops perform a sequence of operations whose total work increases step by step, starting from 1 and going up to n. Each step adds a constant amount, so the pattern of work forms an arithmetic series. This connects the loop structure directly to a basic mathematical idea, where each term grows by the same fixed amount. This script shows how nested loops relate to an arithmetic series. It defines a function that counts how many times an inner loop runs as an outer loop increases from 1 up to some number n. At each step, the inner loop runs as many times as the current step, creating a sequence of 1 plus 2 plus 3 and so on up to n. The script then compares this total from the loops with the arithmetic series formula, which multiplies n by n plus 1 and then divides by 2. Both methods give the same result, demonstrating that the nested loop pattern matches the standard formula for the sum of the first n natural numbers. Geometric loop growth. When a loop changes the amount of work each time by a constant factor, such as repeatedly halving a problem size or doubling a quantity, it follows a geometric pattern rather than a steady arithmetic one. Each iteration's work is a constant multiple of the previous iteration's work. To understand the total cost of such a loop, we must sum all these geometric changes, not just look at the first or last iteration. Recognizing this helps explain why the overall complexity of these loops depends on how the input size scales. Consider a loop that repeatedly shrinks its dataset by a constant factor, such as cutting it in half each time. You first process the full dataset, then a smaller half, then a quarter, and so on. The total work is the sum of these decreasing amounts, and it stays on the same order as the first largest pass. In other words, the initial pass dominates the cost, and the later passes add only a limited extra amount. This is why algorithms that reduce their input by a constant factor at each step typically have total work that grows linearly with the original input size. In geometric growth, each loop iteration does more work than the one before, such as when a batch size doubles or a search radius expands. The early iterations are relatively cheap, but the later, much larger ones dominate the total cost. So the sum of all iterations is close to the cost of the largest step. This pattern appears in processes like viral spread or compound interest, where each step grows by a fixed factor. In algorithm analysis, this means we can often approximate the total running time by focusing on the largest iteration, which leads to exponential or logarithmic complexity classifications. Python code. Geometric loop growth. We want to illustrate how work in a loop can grow or shrink geometrically when each step doubles or halves the amount of work. By comparing the total work across all iterations to the size of the first and last iterations, we can see how these patterns behave. This makes it clear that the total work follows the behavior of a geometric series. Visual tools such as simple plots can help show these relationships in an intuitive way. We begin by importing the math library, which gives us useful mathematical functions and constants for our script. We also import the plotting module from the matplotlib library, which we use to create visualizations. With these tools in place, we can generate plots and graphs that clearly show our data and results, making the analysis easier to understand. The geometric work helper function generates a sequence of work values that follow a geometric progression. It starts from an initial amount and, for a specified number of steps, repeatedly records the current amount and then multiplies it by a given factor. This process scales the value at each step, creating a sequence where each term is the previous term times the factor. After completing all iterations, the function returns the list of these values as the resulting geometric sequence. We set up a loop where the amount of work decreases each time it runs. The starting workload is 1,024 items, and each iteration cuts this amount in half. We plan to repeat this process for 6 iterations. Using these settings, we call the geometric work function to produce a sequence that shows how the workload shrinks over the course of the loop. We set up a loop where the amount of work starts at one item and doubles each time. The doubling factor means that with every iteration, the workload becomes twice as large as in the previous step. We plan to repeat this process for 6 iterations. A helper function then computes the geometric sequence of work amounts using the starting value, the doubling factor, and the number of steps, and stores the resulting list as the sequence of work for the loop. We analyze the halving loop by first summing all the work values in the sequence to find the total effort across all iterations. We then note the first term, which is the initial amount of work before any halving occurs. Finally, we identify the last term, which is the smallest amount of work after repeated halving. Together, these values reveal how the work decreases in a geometric progression throughout the loop. To analyze the doubling loop, we first add up all the values in the doubling work list to find the total work done across all iterations. We then identify the first term in the sequence to represent the initial amount of work. Finally, we determine the last term, which shows the work in the final iteration. Together, these values reveal how the work grows and progresses throughout the loop. The code prints a compact summary of the total work done in both the halving and doubling loops. For the halving loop, it reports the total work along with the first and last terms of the sequence. It then repeats this for the doubling loop, again showing the total work and the first and last terms. This output emphasizes that both loops follow a geometric series pattern in how their work grows or shrinks. We create a visual comparison of 2 sequences using side-by-side bar charts. To do this, we use a plotting function that generates one figure with 2 axes arranged in a single row and 2 columns. The figure size is set to be wide and not too tall, so the bars are easy to see. This layout lets us display the halving and doubling work sequences next to each other, making their behavior easy to compare visually. We visualize the halving work sequence using a bar chart on the first subplot axis. Each bar corresponds to an iteration, with its position given by the iteration index and its height given by the amount of work in that step. The bars are colored steel blue to make them easy to distinguish. The subplot is titled to show that it represents halving work per iteration. And the axes are labeled to indicate iteration index on the horizontal axis and items processed in that iteration on the vertical axis. In the second subplot, we show the doubling work sequence using a bar chart. The horizontal axis runs from 0 to the number of doubling steps, and each bar's height represents the amount of work done in that iteration. The bars are colored dark orange to make this sequence stand out. The title explains that this plot shows the doubling work per iteration. With the x-axis labeled as the iteration index and the y-axis labeled as the number of items processed in that iteration. The code first uses a function from the plotting library to automatically adjust the spacing between subplots so that titles and labels do not overlap. It then calls another function to display the final figure. This lets us clearly view and compare the bar charts for the halving and doubling work sequences side by side. This script illustrates geometric growth and decay in loop iterations using both numbers and visuals. One sequence starts at 1024 and halves the work each step, while another starts at 1 and doubles the work, with both running for 6 steps. The program calculates the total work and identifies the first and last iteration sizes for each sequence, then prints summaries that compare these values to show geometric series behavior. It also displays bar charts that reveal how, in the halving sequence, early iterations contribute most of the work, while in the doubling sequence, the later iterations dominate. Together, these outputs clarify how work is distributed across iterations in geometric series. Bounding sums for big O. When analyzing algorithms with asymptotic notation, we often replace complicated sums that count operations with simpler upper bounds using big O. Instead of tracking every detail, we choose an expression that grows at least as fast as the original, such as a constant times the input size squared for a loop whose work decreases each iteration. This bound may come from something like an arithmetic series, but we do not need the exact total. Just as saying a trip takes less than a day is enough for planning, this rough bound is sufficient to understand how the algorithm's running time grows with input size. To bound the total work of a loop, we compare its sum to simpler, well-understood sums. If the work per iteration grows roughly in proportion to the index, we can estimate the total by multiplying the number of terms by the largest term. If the work per iteration shrinks quickly, such as being cut in half each time, we relate it to a geometric series that converges. The aim is not exact calculation, but to show that the total work stays below some function with a known growth rate, like linear or quadratic, so we can classify the algorithm's complexity. When analyzing nested loops or multi-phase algorithms, it helps to bound each part with a simple function to keep the analysis manageable. Instead of computing every sum exactly, you can use basic algebra and note that when you add two functions, the one that grows faster dominates the total. In a data processing pipeline, this often means the overall work is essentially determined by the largest phase, such as scanning all records, while smaller phases add little extra cost. This lets you focus on the parts that matter most for performance and express the result concisely using big O notation. Python code, bounding sums for big O. We will use simple Python-style loops to show how to count the exact number of operations they perform, and then compare those counts with easy big O upper bounds. By examining these loopwork sums, we can see that even though the exact formulas may look messy, they always stay below simple growth functions that describe their overall behavior. This helps connect precise operation counts with the more general idea of big O notation and shows why big O is a useful way to summarize loop performance. The commented line mentions installing NumPy, Matplotlib, and Seaborn, but also notes that these libraries are not needed for this script. This tells you the script is intentionally simple and relies only on basic Python features. Its main purpose is to illustrate the ideas of bounding sums and big O notation without requiring extra tools or dependencies. The code imports the math library to provide access to common mathematical functions and constants. This allows the program to perform operations such as square roots and logarithms. By including this library, the script is prepared to handle more complex mathematical calculations whenever they are needed. This description explains a function that measures how much work a nested loop performs. It begins by setting a counter for the total number of operations to 0. The outer loop runs from 0 up to, but not including n. And for each value in this range, an inner loop runs from 0 up to, but not including the current outer value. Each time the inner loop runs, the counter increases by 1. When all loops finish, the function returns the final counter value, which represents the total number of inner loop executions and thus the total work done. This function counts how many times a loop can run while its size is repeatedly cut in half. It starts with a counter set to 0 and a variable set to the initial input size. As long as the size is greater than 0, the function increases the counter by 1 and then divides the size by 2 using integer division. When the size reaches 0, the loop stops and the function returns the counter value, which represents the total amount of work done by this halving process. We choose a value of 1,000 for the variable n to represent a moderate input size. This size is large enough to clearly show how the algorithms behave, but not so large that the results become overwhelming. It keeps the printed output clear, readable, and easy to interpret, while still being informative. We analyze a nested loop that behaves like a quadratic function by counting exactly how many operations it performs for a given input size n. The outer loop runs up to n, and for each step, the inner loop runs up to the current index, so the total work grows in a quadratic pattern. We store this exact count of operations in a variable so we can directly compare the real computational work with the theoretical upper bound described by big O notation. To estimate a simple big O upper bound for quadratic work, we treat the number of operations as roughly n times n, which gives n squared. We then divide this by 2 to get a convenient approximate count. This value is easy to compute and still safely larger than the exact number of operations done by the nested loops. As a result, it fits the idea of big O notation, which focuses on an upper limit rather than an exact total. We analyze a loop whose size is cut in half on each iteration by computing the exact number of operations it performs. To do this, we call a function that represents logarithmic style work and pass in the input size. The result is stored for later use and serves as a precise measure of the loop's cost. This exact count is then compared with theoretical upper bounds so we can see how the loop's complexity behaves in practice. To estimate an upper bound for a logarithmic style loop, we look at the base 2 logarithm of n, which reflects how many times the loop runs as the input size is repeatedly halved. We then apply the ceiling function from the math library to round this value up to the nearest whole number, so the bound is an integer. This gives a simple big O-style upper bound on the maximum number of loop iterations and operations. This code reports the exact number of operations carried out by a function whose behavior grows in a quadratic-like way. It does this by counting how many times the inner loop runs as the loop length increases. By printing this count, we can compare the measured work directly to the theoretical upper bound. This helps us see how the actual running time matches our big O complexity prediction. The code prints an upper bound on the work done by the nested loops, calculated as n squared divided by 2. This value is a big O-style estimate that is guaranteed to be at least as large as the exact number of operations. By comparing this printed upper bound to the actual operation count, the code illustrates how big O notation helps us understand and compare algorithm efficiency. This line outputs the exact number of operations carried out by the logarithmic style loop. It relies on a previously computed value from a function that simulates a loop where the number of iterations is cut in half each time. As a result, we obtain a precise count of how many operations were actually executed. We can then compare this count to a theoretical upper bound to better understand the algorithm's efficiency. This line prints an upper bound on the number of operations that grow in a logarithmic way. It uses the base 2 logarithm of n, which matches how we describe logarithmic complexity in big O notation. The key idea is that this bound is guaranteed to be at least as large as the actual number of operations. This makes it a simple and reliable way to understand and reason about the algorithm's complexity. The final print statement explains the main idea of the code. The simple bounds used in the analysis still capture the true number of operations performed by the loops. This connects directly to big O notation, which focuses on how the work grows, rather than on exact counts. Even though the precise number of operations can be complicated, big O gives a clear and practical way to describe the algorithm's growth behavior. This script shows how to compare exact operation counts with big O upper bounds using simple loops. It measures how many operations are performed by a nested loop that grows in a quadratic way and by a loop that repeatedly halves its size, which grows in a logarithmic way. For the quadratic loop, it compares the exact count to an upper bound given by 1/2 of n squared. And for the halving loop, it compares the exact count to the base 2 logarithm of n. When you run the code, you see that the exact counts always stay below these bounds, illustrating how big O notation effectively captures the growth of algorithmic running time. Simple divide and conquer T. Divide and conquer algorithms solve problems by repeatedly breaking them into smaller subproblems, solving those subproblems, and then combining the results. We use a running time function, often called T, to represent the total work the algorithm does for a given input size. This function accounts for the work of dividing, solving recursively, and combining solutions. By studying this function, we can analyze and compare the efficiency and behavior of different algorithms before we implement them. Imagine running a large research survey using a divide and conquer strategy, where you split the surveys into smaller stacks and pass them to assistants, who keep dividing them until each person has a manageable amount. At every stage, there is work involved in both splitting the surveys and later combining all the partial results into one final report. the total effort required for this entire process, from the original large stack to the final merged report, can be described by a function t that depends on the number of surveys. This is similar to how we analyze the amount of work and timing of operations in divide and conquer algorithms. Thinking about the running time function t helps you see the layered work structure in divide and conquer algorithms. At the top level, t represents the cost of solving the whole problem, and at lower levels, it represents the cost of solving each set of subproblems down to the base cases. You can imagine this as a tree whose root is the full problem, internal nodes are subproblems, and leaves are directly solved base cases. T adds up the work across this entire tree, so you can understand how changes in subproblem size or combining work affect the total running time. By defining T to match the divide, conquer, and combine steps, you directly link the algorithm structure to a precise efficiency analysis. Step-by-step recurrences. To understand a recurrence from a divide and conquer algorithm, think of starting with a problem of size n that is split into smaller subproblems, each solved and then combined. The recurrence states that the total work for size n equals the work on all the subproblems plus the extra work needed to divide and combine them. To analyze the running time, you repeatedly expand the recurrence, replacing each term with its own definition, until you reach a base case with a fixed cost. This process lets you see how much work happens at each level of the algorithm and how it adds up overall. When you expand a recurrence, you can track how many subproblems appear at each level and how much work each one requires. This lets you express the work per level in terms of the depth of the process and then add up the work across all levels to estimate the total cost. In many cases, the total work is dominated either by the top level, the bottom level, or is roughly the same at every level. Recognizing which of these patterns applies allows you to approximate the total cost without needing an exact formula. Recurrences are not just abstract math. They model real processes like logistics. You can picture a central warehouse breaking shipments into regional and then local deliveries, and estimate total effort by adding the cost at each stage. When you conceptually expand and combine these stages, you are intuitively solving a recurrence. Thinking this way helps you analyze divide and conquer algorithms without working through every algebraic step. Python code. Step-by-step recurrences. We want to show how to unroll a simple recurrence step by step, so you can see what happens at each level of recursion in a divide and conquer algorithm. At every level, we write out the work done and how the problem size shrinks, then add up the work across all levels. By connecting these levels and their total work, we build intuition for how the algorithm grows with input size and how to express that growth using big O notation. The commented line mentions installing matplotlib, Seaborn, and NumPy, but also notes that these packages are not required for this script. This tells us the script is self-contained and does not depend on external libraries to run. Instead, it focuses on illustrating its main idea using only core Python features. As a result, you can understand and execute the script without setting up additional tools. We define a divide and conquer function that tracks how much work is done at each level of recursion. It takes the current problem size, a dictionary that records work per level, and the current recursion depth. At each call, it adds the current problem size to the total work stored for that level. If the problem size is 1 or smaller, it reaches the base case and returns 1 unit of work. Otherwise, it splits the problem into 2 halves, calls itself on each half at the next recursion level, and then returns the sum of 1 unit of work for the current level plus the work from both subproblems. We begin by choosing an initial problem size, which is the number of items or tasks we want to process. In this example, the starting size is 16. This value serves as the input to our divide and conquer procedure. From there, the procedure repeatedly breaks the original problem into smaller subproblems in a recursive way. We use a dictionary called work per level to track the total amount of work done at each level of a recursive process. As the recursive function runs, we add up the work for each level and store it in this dictionary. This lets us quickly look up how much work happens at any specific level. Overall, it helps us see and analyze how the work is distributed across the different levels of recursion. We use a recursive procedure called divide and count, starting with a problem size of 16, to measure how much work is done at each level of recursion. The procedure takes the initial size, a dictionary that stores the results, and a starting level of 0. As it repeatedly breaks the original problem into smaller subproblems, it records the work performed at each depth. This lets us see how the total work is distributed across the different levels of the recursion tree. We organize the work done at each recursion level by sorting the entries in the dictionary that records this work. The sorting is based on the level number so that we process levels from the shallowest to the deepest. This ordered view makes it easier to see how the amount of work changes as the recursion goes deeper. Overall, it clarifies the progression of computation across recursion levels. The code first prints a header line that labels the columns for the output that follows. It indicates that each row will show the recursion level and the total size of all subproblems at that level. This header gives context so the reader can interpret the numbers correctly. It helps visualize how the total amount of work is distributed across the different levels in a divide and conquer recursion. The code goes through each recursion level in order and, for each one, looks up the total work done at that depth. It then prints a message showing the level number and the combined size of all subproblems handled there. This output lets you see how the work is distributed across recursion depths and shows how the divide and conquer process scales as the overall problem size grows. The final summary line explains that the pattern of work across the recursion levels points to a time complexity of n times log n. At each level of recursion, the total amount of work stays roughly the same, even though the problem is split into smaller parts. This behavior is typical of divide and conquer algorithms, where the work at each level is proportional to the input size, and the number of levels grows in a logarithmic way. Together, these observations justify the overall n log n complexity. This script illustrates how a divide and conquer algorithm works by repeatedly splitting a problem of size 16 into 2 smaller halves until each subproblem is of size 1 or less. then combining the results. As it runs, it records the total amount of work done at each level of recursion. The output shows that the combined size of all subproblems stays consistent across levels. This pattern indicates that the overall running time grows on the order of n times log n, which is typical for divide and conquer methods, and helps visualize how the work is distributed throughout the recursion. Linking code and recurrences. To connect a divide and conquer algorithm to a recurrence, first describe in simple terms how the algorithm works. Then translate that behavior into a mathematical pattern. Focus on how the input size shrinks, how many subproblems are formed, and what extra work is done outside solving those subproblems. For example, in a sorting algorithm that splits a list, you divide the list, sort each part, and then combine the results. This naturally leads to a recurrence, where the total cost equals the cost of the subproblems plus the cost of combining them. By clearly stating this process, you can identify the recurrence that models the algorithm's performance. When analyzing divide and conquer code, connect each part of the control flow to the recurrence it implies. The recursive calls tell you how many subproblems are created and how large they are relative to the original input, while the non-recursive work shows the extra cost done at that level. For instance, if the code splits data, recurses on each piece, and then merges the results, the recurrence has terms for each recursive call, plus one term for the merge work. In conditional cases, like spatial searches, there may be fewer recursive terms and more emphasis on boundary checks in the non-recursive part. Thinking this way lets you group operations into recursive work and overhead, which together define the recurrence. Linking code to recurrences is a key technique for connecting how an algorithm is written to how its running time grows with input size. You can start from real tasks, derive a recurrence from the code, and then solve it to predict performance. Or you can begin with a desired recurrence and design code that follows it, ensuring the algorithm scales the way you want. With practice, this translation becomes intuitive, so you can mentally move between the code, the recurrence, and the overall strategy of the algorithm. Python code, linking code, and recurrences. We want to connect a recursive algorithm to its time complexity by relating the code to its recurrence relation. Using a merge-sort style process, we repeatedly split the input into two halves, solve each half recursively, and then merge the results. As we do this, we count the operations performed at each level of recursion. These counts should match a recurrence where the work for a problem of size n equals twice the work for size n divided by 2, plus a term that grows linearly with n. By printing and examining these counts, we can see how the recursive structure leads directly to this time complexity relation. This comment explains that no extra installations are needed for the demonstration. It tells the reader that the code is self-contained and does not rely on any external libraries or packages. As a result, the code can be run right away without additional setup. This makes it easier for users to quickly test, explore, or modify the example. In this version of merge sort, we define a function that both sorts a list and counts how many comparisons it makes. The function takes a list as input and first checks a base case, if the list has 0 or 1 element. In that situation, it simply returns the list as it is, along with a comparison count of 0, because no comparisons are needed. This base case gives the recursive algorithm a clear stopping point and lets it handle the smallest subproblems directly. In this part of merge sort, the code first finds the middle index of the list by dividing its length by 2, which determines how to split the list into 2 halves. It then recursively applies the merge sort procedure to the left half, producing a sorted sublist and counting how many comparisons were made. The same process is repeated for the right half, again, obtaining a sorted sublist and a comparison count. By breaking the list into these smaller halves and sorting each one separately, the algorithm sets up the final step of efficiently merging the 2 sorted halves back together. To begin the merge step, we create an empty list that will hold the combined sorted elements from both halves. We then set up 2 index variables, one for each half, to track our current position as we move through the elements. In addition, we maintain a counter that records how many comparisons we make during this process. This comparison count is important for analyzing the efficiency of the merge algorithm and relating it to its recurrence relation. The code uses a loop to merge the 2 halves of the list while both still have elements. This loop is the non-recursive part of the algorithm and corresponds to the constant times n term in the recurrence relation. On each iteration, it increases a counter that tracks how many comparisons are made. It compares the current elements from the left and right halves, appends the smaller one to the merged list, and advances the index in that half. By repeating this, it produces a single sorted list and records the total number of comparisons required. After the main merging loop, the algorithm adds any leftover elements from the left half to the merged list, making sure none are missed. It then does the same for any remaining elements in the right half. This final step completes the merge by including all elements from both halves and preserves the sorted order established by the earlier comparisons. This code tracks how many comparisons are made during merge sort. It adds the comparison counts from sorting the left half and the right half of the list, then adds the comparisons used when merging those halves. This total follows the merge sort pattern of twice the work on half the list size plus an extra amount that grows in proportion to the list length. The function then returns both the fully sorted list and this total number of comparisons. The function uses a helper to run merge sort on lists of different sizes so we can study its behavior. For each size, it builds a list of numbers in descending order to create a predictable test case. It then calls the merge sort algorithm, which returns the sorted list and the number of comparisons performed. By repeating this for each input size, we can see how the number of operations increases as the list grows, illustrating the time complexity of merge sort. The code prints a message showing the size of the list being sorted and how many comparisons the merge sort performs. This information illustrates how the number of operations grows with the input size. It connects the actual behavior of the algorithm during execution with the recurrence relation that describes its time complexity. In this way, the output links practical performance measurements to the theoretical analysis of merge sort. We choose input sizes of 4, 8, 16, and 32 to show how the work done by merge sort grows roughly in proportion to n times the logarithm of n, where n is the input size. For each of these sizes, we run a merge sort demonstration that sorts a list of numbers arranged in descending order. As it sorts, the demonstration counts how many comparisons are made. By comparing these counts across different input sizes, we can see how the number of operations increases with n, and how this behavior matches the theoretical time complexity of merge sort. This script demonstrates merge sort while counting how many comparisons it makes during sorting. It uses recursion to split a list into smaller parts, sort them, and then merge them back together. The goal is to connect this recursive structure to the algorithm's time complexity, which grows like a linear term applied at each level of splitting the list in half. The code runs on descending lists of increasing sizes and prints the number of comparisons for each, showing the characteristic n log n growth pattern of merge sort. This links the practical behavior of the implementation to its theoretical performance. In this lecture, you learned to use basic properties of logarithms and exponentials to interpret algorithm complexities, evaluate simple arithmetic and geometric series that arise from loop counts, and solve or approximate simple recurrences that describe divide and conquer algorithms. In the next module, Module 3, we will go over core data structures.
Thank you for your attention. See you all in the next lecture.